now today look at the idea of the derivative of a special type of function called an exponential function. And I want to, first of all, before we even look at derivatives, I want to look at what an exponential function is to make sure that we're all thinking of the same type of equation. And plus, it's very easy to confuse this type of equation with one that we've already done before. Okay? We have done, excuse me, what are called polynomials. And polynomials can also be referred to as power functions before. Examples of polynomials or power functions might be things like y equals x squared, or f of x equals x to the fourth. You know, any of these types of equations, we know how to take the derivative of this. Okay? What we want to look at here today is exponential functions. And an exponential function takes the form, or it looks like y equals 2 to the x, or f of x equals 4 raised to the x. Okay? So this is the major difference, is that the base and the exponent have switched positions here, and we do not have the same process for a derivative down here as what we had up here. Okay? Now, to start out with, well, let's look at an exponential function. Let's just look at 2 to the x. Okay? Start out with one that's somewhat easy here. Okay? And let's look at that definition of limit that we had, about a couple weeks ago here. It said that if we ever wanted to find the derivative of a function, we could follow this slope formula here on our way to calculating the derivative. And so that's what we're going to do here today. We're going to start with this particular slope formula, and let's work with 2 to the x. Let's start substituting this function into the slope formula and see what comes out. Okay? All right, first thing I want to do is evaluate my function at x plus h. So instead of just having 2 to the x, I have 2 to the x plus h. I'm evaluating it at a point just a little bit to the right of the x value that I want. Okay? Minus the original function, so minus 2 to the x, and then all divided by h. At this point, if I tried to substitute in 0, I would end up with 0 on both numerator and denominator, so I would be stuck. Okay? So I need to come up with a different approach. Well, what I can try to do is this. Okay? I want to look at rewriting this first factor. Okay? I want to split it apart using a little bit of algebra here. Okay? And my clue is off to the side, if I had some equation or some expression, if I had 2 to the 5th, how could I rewrite 2 to the 5th? Okay? I could write it as 2 times 2 times 2 times 2 times 2. I could write it as 2 times itself 5 times. Okay? I could also rewrite it, I don't know why we would want to do this, but we could rewrite it in a form where we might want to pair 2 of them together, and then we might want to pair the other 3 together. So I could also write 2 to the 5th as 2 squared times 2 to the 3rd. Okay? And the reason I bring this up is because now I want you to notice how that is similar to what we have over here. And the reason I say that it's similar is because then I could rewrite this as 2 to the 2 plus 3, couldn't I? Okay? So now if we try to split this apart, what will this look like if I try to split this exponent apart here? 2 to the x times 2 to the h. Good. Okay? Whenever we have addition in the exponents, like here we've got 2 plus 3, we can split that apart into multiplication. And that's the algebraic property I was trying to get across here. All right, so now let's just rewrite the rest of this. Okay? The reason I wanted to do that is because now what factors out of the first term and the second term? I can now factor out a 2 to the x. Okay? So I have 2 to the x coming out. 2 to the h is still left over from the first factor, minus 1 left over from the second factor. Now, it doesn't seem like we've made a whole lot of progress. Okay? But the point that I wanted to get across is this. Okay? Not that this is going to help us with an answer, but just conceptually here, notice that we started with the function 2 to the x. And we started working with its slope, and look what happens as part of the answer. part of the answer to the derivative is 2 to the x again. Okay? So that's the first point that I want to make. Okay? So what we've got at this stage, I'll have to come up here to the top, the next row to continue this. Okay? If the original function is 2 to the x, part of the derivative is also 2 to the x. Okay? Now the thing is, that's not the whole derivative because we've still got all this other stuff with h's in here to consider, but we've got part of the answer. Okay? Now the question then becomes, well, what does the rest of this answer yield for us down here? Okay? And at this point, this is an equation which we don't have a lot of good algebraic techniques to solve, and so what I'm going to have you do is plug in some small values for h. Remember, limit h gets really close to 0 here. So on your calculators, okay, I want you to plug in a really small value for h in both this location and this location. Make sure you use parentheses up in the numerator, and let's see what that value is. Let's see what this whole quotient turns out to be. Okay, that's what we're interested in. Yes?
How come that 2 to the x and the 2 to the x don't cross out? Why can't you just get rid of?
Well, I don't have one in the denominator. The question was, why can't we just cancel those off? Okay, well, I can definitely factor one of them out from the numerator because I have one in both locations, but I don't have one down in the denominator to be able to cancel it off. Okay, a similar example, algebraic example here. What if I, instead of having 2 to the x's, what if I just had numbers? Okay, what if this was a 7 times 3 minus 7? Okay, 7 times 3 minus 7, kind of a similar idea. Okay, I can't really cancel the 7 off, but I can factor it out from that group. Okay, so that's the difference there. All right, my question then that I posed before, what was this value of what I have in dots here? Did anybody get that value? What do we get when we substitute in a really small value for h into numerator and denominator? And it won't be a really nice number. Okay, it'll be a decimal, but
0.69.
yeah. Okay. And I'll just go ahead and put it up here for right now. Okay, turns out to be 0.693, okay, or something in that neighborhood, which doesn't really help us a whole lot because it's not really that nice of a number. Okay. Now, if any of you recognize what this number is, then you're a lot smarter than I am because I didn't recognize it the first time I saw it either. Okay, but there is a nicer way to represent this number. Okay. Now, my clue on what that nicer way to represent the number is this. I'm going to kind of just let the cat out of the bag here. But notice we're working with what are called exponential functions. My clue, what's the opposite of exponential functions? Starts with an L. Logarithms. Okay? Logarithms are the opposite. And so my question is, just try this on your calculator. Okay, let's see if we can just stumble into it here. We've got two different kinds of logarithms. Okay, we've got a regular logarithm, and then we've got a natural logarithm. Okay, I want you to punch those two numbers into your calculator and see what you come up with. Okay, the one that matches up with this 0.693 happens to be the natural log of 2. Okay, and so this decimal, this mystery decimal that they figured out really is the natural log of 2. Okay, and that's a lot nicer. Now, what if we were doing a different function? What if we, instead of doing 2 to the x, what if we were working 4 to the x? Now, even without going through all the definition here, what needs to be the first part of the derivative? Just kind of follow our pattern from up here. Yeah, 4 to the x, okay? Looks like the derivative of 2 to the x had a 2 to the x component in it, and so we might guess that 4 to the x would have a 4 to the x component in it. Okay? Now, what do we think this number might be over here? If this one was the natural log of 2, it might be reasonable to guess that this one could be the natural log of 4. Okay? So we're questioning this right now. We're not sure if this is correct. How are we going to be certain that it is correct? Okay? Well, if we were to go through and replace all these 2's with 4's, just redo the same problem with 4's in it, okay, I would have a 4 to the x here, so that's good. That matches up. Okay, and then down here, I would have 4 to the h minus 1 divided by h. So what I need you to do, just to verify this, retype in, again, a really small number for h, put 4 to that small number minus 1 divided by your small number, and let's see if that answer is really close to the natural log of 4. Okay, this is, again, very informal because we're not in a math major class here. We're just trying to see, does this continue to work, this pattern? Okay, and I see some of you starting to shake your head yes, that you agree, yeah, this is working. Okay, and so in general, our definition here for a function of exponential form, so if we have some number a raised to the x power, doesn't matter what the number is for a, as long as it's positive, okay, because we usually don't work with negative exponential functions, okay, then the derivative function is a to the x times the natural log of a. And so it's just the same function itself times some natural log, just times some constant number. Okay? This is our definition, or this is one of the definitions that we're going to pick up here today. Okay? All right, now, the second example that I want us to look at is a special type of exponential function, e to the x. E is a number just like 2 and just like 4, so we should be able to calculate a derivative for e to the x. Okay? According to our definition, what should the derivative of e to the x be? Okay? Well, the first part of it needs to be e to the x, and then times the natural log of e. And you might want to type this in your calculator if you don't know, but type in the natural log of e into your calculator. Now, on Texas Instruments calculators, you might have to put a 1 here because I think it automatically puts a caret and it's waiting for you to input a power. So just ln of e to the first. What is it? It's a 1, isn't it? Okay. So whenever we multiply by 1, well, that doesn't change anything. So we really don't need to even write the natural log of e. And so this is one function. This is the only function that we know of in mathematics that does this, where the original function and its derivative are exactly the same thing. Okay, the original is e to the x, the derivative is e to the x. Okay? Now, what that means is this. It's a really strange situation, but it just means that if we looked at how fast the y values were going up, okay? And so if we look between 1 and 2 and 3 and just looked at how fast the y's were increasing, if we also looked at how fast the slopes were increasing, they'd be increasing at exactly the same rate. The y values and the slopes are changing at the same rate. And like I said, that's the only function in mathematics that we know of that does this. Okay? So this is a really simple derivative to memorize. E to the x is just e to the x. Okay? All right, so that's our second definition. Now let's look at a couple of examples here. You know, what if we do something like this? What if we have e to the 4x. So what if we change up and don't have just an x up in the exponent? What if we have something like 4x? How does this affect our result? Okay. Well, this is where we talked about chain rule before. That's where this process comes into play. Okay? Because what we had to do on the, just again off to the side here, if we had an equation like x squared plus 2x raised to the 4th, okay, well, we know that we had to take the derivative of the outer function first. Okay, so we decided, well, when we're taking the derivative, we bring this 4 out front, and we leave everything the same raised to the 3rd. That was the derivative of the outer function. And then the chain rule said, well, now we've got to multiply by the derivative on the inside. We're going to need to do a similar process up here, okay, where the outer function is going to be e to some power. E to some power is the outer function, and then the inner function is going to be the little 4x up here. Okay? So here's what I mean by this. Okay, first of all, what's the derivative of e to some power? What's the derivative of e to some power? Well, just e to some power, isn't it? Okay, that doesn't change. The derivative of e to the x is e to the x. So the derivative of e to the 4x, or at least part of it, is e to the 4x. Okay, that's the outer function on the chain rule. Now I need to come back and multiply by the derivative of the inner function. And what's the derivative of 4x? Just 4. So I need to multiply this by 4, and that's my derivative for something like e to the 4x. Okay, so we have this chain rule involved now. Okay. All right, let's look at a few more examples where the chain rule is in on these exponential functions. Okay. What if we've got e to the x squared plus x, and we want to calculate the derivative of this particular function? Okay, well, first of all, what's the derivative of e to some power? E to that power, exactly. That's the outer derivative. And now I need to multiply by the inner derivative, which happens to be what here? What's the derivative of the function itself? 2x plus 1. Yes. And this is my answer. Okay? So exponential derivatives, really not that hard. You basically just have to rewrite the function and then multiply by the derivative of that inner function there. Okay? What if we look at an example like this? F of x equals 2 to the, I don't want to make it too bad yet, 2 to the 3x squared. Okay. All right, my outer function is 2 to some power. So the first question is, what's the derivative of the outer function? What's the derivative of 2 to some power? Well, I have 2 to that power. That's the first part of it. What do I need to multiply by because this is not an e? I need to multiply by the ln of 2. Okay? So this, all of this, what I'm doing up to this point is just taking care of the outer function. 2 to some power, its derivative is 2 to that power times the ln of 2. Okay, so that takes care of the outer function. Now I look in the inner function, the 3x squared, and what's the derivative of it? 6x. And so all of this together is the derivative of the original function that I specified here. Okay? In terms of simplifying, you probably won't be able to do very much with this. Okay? Because this is still a power function, or still an exponential function, so we can't do a whole lot with it. Okay? The x's are up in the exponents. Here the x's are down in the base. And usually natural logarithms, we just leave them. We usually don't multiply them through. So this is probably simplified about as good as we can get. Okay? All right, what if we've got this one? This will be another example here. Well, let me change it from a 2 just to something else. What if this is a 5? 5 times the square root of x, or 5 to the square root of x. Okay? All right, well, first of all, what's the derivative of 5 to some power? 5 to that power. Okay, so 5 raised to the square root of x is part of the derivative. Okay? Then because this is a 5, the other part of the derivative is to multiply by the natural log of 5. Okay? Okay. Then, yep, exactly. Then I want to look into the inside function, the square root of x. And I question, well, what's the derivative of the square root of x? Okay? And that derivative, we said the other day, was 1/2 x to the negative 1/2. And so all of this put together is the derivative function that we are looking for. Okay? And this is the hard part. To me, now that we've got enough different types of functions, okay, the hard part is recognizing which basic rule do I need to use. Should I be using a product rule? Should I be using a quotient rule? When does the chain rule get used and when does it not get used? Okay? But to me, the thing is, as I look at these equations, notice that they are a number raised to a variable power. And that's the clue that separates today's problems from some of the other ones. Okay? It's e to some power, 2 to some power, 5 to some power. That's your clue that I should be using a definition like we've been talking about here today. Okay? All right. Let's continue to look at some examples here. What if we've got one like this? X minus 3 quantity squared times e to the 2x. All right, so my first question is, as we look at this function, along the discussion that I was just having here, what's the major rule that we need in order to take the derivative of this equation? Or what's one? There's going to be more than one here, but what's one of the rules we need? And my clue would be, can I look at this as just one big single function, or is it a combination of two functions put together? Okay, definitely a combination of two functions. Okay, how are the two functions joined together? Well, we don't write it in here usually, but we have a multiplication sign. So what's the major rule that I need to use here? Product rule, right. Okay, I have some function times another function. And so that's my clue. This needs to be a product rule situation. Okay? All right, now let's go ahead and actually work through the product rule. Just to remind ourselves, how do we take the derivative of a product rule? We take one of the pieces times the derivative of the other, plus, and then we switch the order around. Okay, so we remind ourselves of that. Okay, so let's start working through this. Okay, I'll write the first piece as it is. Okay, now I need to multiply by the derivative of the second piece. All right, derivative of the second piece looks like what we've been doing today. What's the derivative of e to the 2x? E to the 2x, and then times what? Times a 2, right, okay? That chain rule that we just talked about up there, okay, e to the 2x times 2. Okay, plus, then I rewrite the second part as it is, e to the 2x, and I multiply by the derivative of the first part. Okay, and so my question is, what's the derivative of the first piece? Okay, 2 comes out in front. X minus 3 is now raised to which power? What do we do with exponents? We drop them by 1. Okay, so it's now raised to the first. And then my question is, I look on the inside of the function, because I've got a chain rule here. What's the derivative inside this function here? No? 1. The derivative inside, the slope of x minus 3 is just a slope of 1. So I have a chain rule, but the chain rule happens to just be multiplied by 1. So it really didn't change anything. Okay? But I did have a chain rule. Now, in terms of simplifying, we do want to simplify product rules because a lot of stuff factors out. Okay? What can I factor out? Or what's one of the things I can factor here? Okay, I heard somebody say we can factor out a 2. And I agree with that. We've got a 2 in both spots. Okay, so that's been factored out. What else can be factored out? X minus 3. I can take out one of those factors. I got 2 of them here, so I've reduced it to 1. And I've took this factor out of the equation. Okay. What else? E to the 2x comes out. All right, very good. And that looks like all the factoring. Now, what is left that did not get factored out of the first term? Okay, I have another one of these x minus 3s here. Okay, so this is x minus 3. So that takes care of the first term. What did not get factored out of the second term? Just a 1. Okay, so I've got a plus sign and then a 1. Okay, and so I'm not going to rewrite this. I'm just going to go in and clean this up here real quickly. X minus 3 plus 1 just happens to be x minus 2, doesn't it? Okay. Why do we want to simplify this? Because, again, as we progress here, we will be looking to set these functions equal to 0. We want to know where does this graph have peaks or valleys. Okay? And so if we got to this point, and I wanted to know where does this graph have peaks or valleys, where's one place where we have one? Okay, because of this factor, x minus 2, I can tell that at x equals 2, we have a peak or valley. Okay? And the reason is because if I take 2, if I sub 2 in all the places here for x, okay, what do I have to get for an answer? I have to get 0 because this will be a number, a number, a number, but then this will be times 0, won't it? So whatever times 0 is just automatically 0. Okay, where else do I have a peak or valley? According to this, I have one where? At 3, okay, for the same reason. Okay. Do I get any solutions off of this factored out 2 here? can 2 ever equal 0? No, so I don't have to pick up any solutions from that. And then the last question, can this e to the 2x, can that ever equal 0? Okay, and this will just be a little bit of a review for you here. The answer is no, it can't. But if we ever look at a graph of e to some power, okay, e to some power always looks like this, or something along these lines. But the most important thing is that e to some power never crosses 0 down here. And so we never pick up any extra solutions on e to some power graphs. Or even if this isn't an e, even if it's a 2 to some power, that graph never crosses the axis, so we don't pick up any extra solutions. Okay? They're part of the derivative, but they don't give us any other answers. So in this particular place, this original function that we started with would have 2 peaks and valleys, okay? And they're at 2 and 3. All right? Okay, let's look at another one here. What if we look at this question? E to the x plus e to the minus x divided by x. All right, and again, we just care about finding the slope of this particular graph here. Okay, what's the major rule that I need to be concerned with here? Okay, this is a quotient rule example, right? That's the major rule that I'll be thinking about now. As I go through the quotient rule, I may have to remember some of these rules we talked about for derivative of e to the x. Okay? All right, so what's the quotient rule tell me? What do I start with? Okay, derivative of the numerator. Okay? And so I need to start by taking the derivative of the numerator. What's the derivative of e to the x? E to the x. What is the derivative of e to the negative x? E to the negative x. Now, here's the thing though. Okay? What's the derivative up inside this function though? Negative 1. Right, so I need to have e to the negative x times negative 1. Okay? All right, so that's the derivative of the numerator. Okay? I'm going to put that in a bracket here. Times what? Think about the quotient rule here. I take the derivative of the numerator times what? The denominator. So I'm just going to rewrite this x. Okay? All right. What sign goes here? Minus. Okay? Then I need to switch the order around. I need to take the derivative of the denominator, which happens to be just a 1, right, times the original numerator. So e to the x plus e to the minus x. Okay? All divided by what? Divided by denominator squared. So divided by x squared. All right, as far as simplifying on this one, I don't know how much it's going to work because, you know, if this negative 1 basically turns this into a subtraction. So I get e to the x minus e to the negative x. Here it's e to the x plus e to the negative x. So I really can't join those together very well. This one's also got an x distributed through. This one has a 1. So I don't know if spending time simplifying this is going to be very fruitful. Okay, so we'll just leave this example as it is. Okay. All right, so there's one with quotient rule. Okay, what if we've got this one right here? S of t equals 5 times 7 raised to the square root of t minus 2. All right. Little different element involved in this one here. Okay, the different element involved is that the 5 we have the whole function. You know, we have this 7 raised to some power function, but then it's multiplied by 5. What do we do with multiplication in derivatives? You know, when I have, just off to the side, a really simple example, what if I had 3t squared? What do I do with this 3? Well, it just kind of stays there, doesn't it? And it ends up getting multiplied by 2. Okay? So the same thing is going to happen in this example. That 5 is just going to stay out front because it's multiplied by the function. Okay? So it kind of just stays out there as part of the derivative. Now I look at 7 raised to some power. What's the derivative of 7 raised to some power? 7 to that power times what? There's one more part of this derivative. 7 to the power times ln of 7. Right. Okay. That's the derivative of some number raised to a power. Okay. So don't forget this ln of 7. All right. So 7 raised to the power is derivative. We've taken care of that. Now I've basically done with the 7. I've taken that part of the derivative. Now I just look up here in the exponent. What's the derivative of the square root of something? How do I need to think about the square root? As what? To the 1/2. Okay, so what's the derivative of the square root of this? (1/2) t minus 2 to the negative 1/2. Exactly. Okay. Now, this one actually goes one more layer deep because now I've taken care of the 7. I've taken care of the square root derivative. Now I've got to look inside the square root. Does that also have a derivative? Yes, it does. It happens to be what? Happens to be a 1. But had this been something more complicated, like had this been a t squared in here, okay, then everything would have stayed the same. I would just have t squareds everywhere. But now what would I have to multiply by here at the very end? What's the derivative of this inner function? 2t, right. Okay, so this would have been a 2t out here at the end. So this one actually had many, many derivative rules all in the same one. First of all, it had this power rule that we've been talking, or this exponential derivative we're talking about today. But it also had a couple of layers of chain rules. Okay? It had the original function, then it had a chain rule, then it had another chain rule in it. Okay? And this is where derivatives get really messy at times. Okay? This is one of the more harder ones that we will do here, but just to expose you to them, as you'll run across one or so on your homework probably, they can get to be pretty messy pretty quickly here. Okay? The reason we won't do a whole lot with these types of derivatives is that, again, our goal is going to be put a 0 in on this side, set it equal to 0. And if we get too much of a mess over here, it's really difficult to solve those types of equations. Okay? Whereas if we look at an example like the one we just did before, this one is not so bad because we got some nice factors here. We could actually set it to 0 and come up with a reasonable answer. Okay? So we may get a little bit of practice with these messy derivatives here, but for the most part, they're going to be a little bit nicer by the time we're finished. Okay? All right. I'm going to put an example up on the overhead here. Get the projector back on. Okay, and as it's focusing in here, I'll erase the board and make some room, and then we'll take a look at this example. Let's see if I can get it to focus better here. Okay, maybe I need to shoot this straight down. Okay. There we go, that's a little better. All right. It says after the introduction of a new product for tanning without sun exposure, the percent of the public that is aware of the product is approximated by this equation. Okay? A of t equals 10 times t squared times 2 to the minus t, where t is in months. Find the rate of change of percent of the public that is aware of the product after the following number of months. Okay? And I'm going to go ahead and ask some other questions as well, not just the one that's posed here. Okay? My first question that I'll ask is just to calculate A of 2 and then explain to me what A of 2 means in this problem. Okay? So I actually want the calculation, and then I want to put a label to it, describe what it means. Okay? Well, A of 2 is a pretty simple calculation. All we need to do is substitute 2 into that function and see what we come up with. All right, so let's do that here. We can actually do this probably in our head here, okay, because 2 squared here is just a 4. And then 2 to the negative second. Okay, quick way to do this in your head. Well, first of all, what's 2 to the second? That's 4, and then the negative just means that 4 goes down to the denominator. So this is 1/4. Okay? So what's 10 times 4 times 1/4? Yeah, sure, it's just 10, right? The 4 and the 1/4 cancel off. Okay, so the answer for 2 is equal to 10. Now, what does this mean? Well, first of all, what is 2 in this problem? That's time, and in this case, it is in months. So what this answer is saying is that after 2 months, okay, what's 10 after 2 months? Okay, 10 is a percent, right? In the problem, it talks about this being a percentage. So after 2 months, 10% of the public is aware of this product. So in other words, they've probably started to do some advertising, and after 2 months, only about 10% of the public has seen the ad and is aware of the product. Okay? Now, what would we expect to happen if we started plugging in bigger and bigger numbers here? Just intuitively, we would expect that probably after 4 months that this percentage will be a little bit higher, won't it? Okay? You know, we would expect more people have seen the commercial by the time 4 months have gone by instead of 2. Okay? All right, but that's plugging into the original function and then giving a description of what that number means. Okay, now let's take the next step. Now let's calculate a prime of 2. Let's calculate the derivative, and then we'll put a number to that, or put a label to that number, see what it refers to. Okay? All right, as we look at the original function, what's the major rule we need to use here? Product rule. Okay? We've got a polynomial out here, 10t squared, and then we've got a exponential function over here, 2 to the negative t. Okay, so product rule. We start out by writing the original, or one of the pieces, times the derivative of the other one. All right, what's the derivative? 2 to the negative t. Well, 2 to the negative t is part of it, and then what's the chain rule tell me to multiply by? Maybe I should, let me back up here a second. I want to try to go in the same order I've been going in all day here today. 2 to the negative t, part of the derivative is 2 to the negative t, but then what else needs to go here? ln of 2, right. Okay, I'll go in the same order I've been doing, sorry. Okay, so this is part of the derivative, but now this negative t also has a derivative, and what is it? Negative 1. So I have to multiply here by the chain rule, which tells me multiply by negative 1. Since this wasn't just a t, since it was something else, it also has a derivative, so I have to multiply by it as well. Okay? All right, so that's the first times the derivative of the second, okay, plus the second, 2 to the negative t, times what's the derivative of the first? 20t, right, that was the easy one, yeah. Good. All right, so we've got all this set up. Now I should probably have a t here because right now we haven't done any substituting, okay? But our ultimate goal is now let's go ahead and sub in 2, okay? In for all the values of t into this function. And I'm going to let you do that because we don't have as nice of numbers this time, okay? We can do some of this in our head, though. If I plugged in 2 right here, this would be a what? Be 10 times 4 or 40. Okay, so this whole piece is 40. 2 to the negative second, we already said that was 1/4. ln of 2, we'll just have to punch in the calculator. And then I've got a negative sign, so I got a negative out in front here. Okay, over here, this 2 to the negative t is 1/4 again. 20 times 2 is 40. So maybe this will simplify it a little bit. What is the value of this answer? Negative 3.1? Oh, 93.1, okay. All right, so we got, on the original function, we got a 10. Now down here, we get a 93.1. And so right away, we may question, is this right? Did we make a mistake somewhere along the line? Okay. And my answer to that is, no, we probably didn't make a mistake. This probably makes some sense. Okay? What's this 93.1? What's the label for it? Okay? Well, remember that when we do a derivative, we always get a label with a division in it. You know, it's something per something. Okay? Because a slope, that's what a derivative or a slope is. It's the y label divided by the x label. Okay, what was our y label in this problem? What's the a? What was the a in this problem? That was percent, right. Okay, so this is percent. And then what was the t, or the x coordinate of this problem? Months. All right, so the label for this is percent per month. So what we're saying is that when we get close to 2 months, okay, we are having a rate of change of 93% per month. Okay? Can anybody put that into better English there for me? I mean, this isn't bad, but we can probably say it a little better. What's happening to the percentage of people that are viewing this advertisement? It's going up by how much? It's going up by 93%. And doesn't that, wouldn't that be reasonable? At the very beginning of the ad, we only had 10% of the people that had seen this. But what's happening to the number of people that are actually viewing this? It's going up, isn't it? And it's probably going up pretty quickly. So maybe if we had to look at this and guess, what might we guess the value is for a of 3? This is pretty close to 100%. So I'm just going to round it up to 100% real quickly. Okay? If this was 100%, what percentage of the population would we guess has seen this at the end of 3 months now? Wouldn't we guess that it's up 100%, so we might guess this is up another 10%, so around 20%. Okay? I'm going to say it again to see if this makes sense here, because this is the real goal of the course is, we can get all these numbers, and this is great, but do they mean anything for us? Okay? It's saying that at 2 months, 10% of the population had seen it. Okay? If I go up to 3 months, I would guess that around 20% of the population has now seen it. And if I went from 10% to 20%, isn't that like a 100% jump? A rate of change of 100%. Well, that's about what we have down here. We have a 93% jump in the amount of people that have seen this. So we might guess that around 19% of the population has now seen this advertisement. And if you want to double check this, to see how close we are, go back into this function and plug in 3 instead of 2. And my guess is that this answer will be somewhere in the neighborhood of 19 or 20%. Okay? And that's the meaning of this derivative down here. Okay? All right. That'll take care of our time here for today. We'll see you in a couple days.